Okay, well, welcome. Today I'm going to talk about the power of machine learning and graphs. And so here's the things I'm going to talk about. First, I talk about our vision for cognitive computing, and part of the vision is to make sure that the output of your analytics go back into the graph. So I'll talk a little bit about the importance of that. Then I'll show you some examples, in this case from healthcare. If I have more time, I could show you more examples. And then I'm going to talk about how we make it easy to do data science with AllegroGraph. Yeah? So we'll talk about two AllegroGraph open source packages. The first one is AllegRo with a capital R. It's made by a partner in New York. It's an R interface to AllegroGraph. And then I'm going to do a demo with that. And then I'm going to talk about an open source package that we provided, Franz. It's called Python Anaconda, and it's a Python interface to AllegroGraph, and it's installable with the data science environment Anaconda. And then I will conclude with some future work and future presentations that I'm going to give in the near future. Okay, so let me first talk about our vision of cognitive computing and how. Well, let me just first start with this. So if you look at the history of data science that you see about 10 years ago, we're all working with structured data, and then we were doing a little bit of data science on top, and basically the output of your data science would go to human beings, to scientific publications, to regular reports. And actually, when you look at the word cloud here, I think that 10 years ago, probably not even, only 10% was actually really available to use. Then about 8 years ago, people started saying, you know what, there's actually far more information in our enterprise if we also would look at the unstructured data. So that's when we saw the rise of natural language processing to get entities out of text. We saw the rise of key value stores, NoSQL, big data, Hadoop, Internet of Things. So that was the next thing that people started adding to their data infrastructure. And then 4 or 5 years ago, we saw the rise of knowledge graphs and companies including knowledge in their data infrastructure. One of the best examples is obviously Watson, yeah, where they added almost anything from the linked open data cloud to their data infrastructure, actually as triples at the time already, but also terminology systems, ontologies. And that's just Watson, but every other big company, whether it's Google or LinkedIn or Yahoo or Microsoft, they're all working on their own big knowledge graph as part of all the other data that they also have. Okay, and then much more recently, and this is what our talk is going to be about today, is that we saw that the output of the data science that we do on top of our learning not only goes to, well, people and reports, but it actually goes back in your data infrastructure. Yeah. So you do your data science, you get results, and you put it back in your data. And to my knowledge, most people do it do this no longer in relational databases, but they do it all with graph databases, and preferably semantic graph databases. Yeah, if you want to include knowledge. So, and this is our vision of cognitive computing. But as I said before, I want to really talk about what is the value of putting your results back in the database. Well, if you look at the current state of analytics, yeah, as I just said, the output of data science usually goes to reports and publications and human beings. But most companies don't have a formal trace where the data came from. Yeah, no formal link to the actual methods you used. What kind of R script do you use? What Python method? What Spark method? You don't know who did the analytics or when you did it. You can't go back in time and see, so I made this decision based on machine learning, but what was the data that it was based on? Yeah? Or, hey, I get a different result now from a year ago, but you can't even do it right now because you don't store the results. And so the core of it is actually that you can't use your previous research as a building block for further research. And then in addition to that, what we also see is sometimes the output of data science is in itself so big that it is hard to even figure out what you discovered in your data science methods. Yeah. So the output of your data is not queryable, and you can't, as a human being, not really easily discoverable what's in your result sets. Now, what we're proposing is to enrich the graph that you already had with analytics. Because if you do that, if you really put the output of your analytics back in your data infrastructure, you get true machine learning. Yeah, your results become data. You can get layers on analytics on top of your earlier data. You get a formal provenance for all your results. Yeah, so you can link to the actual data you used, the methods you used, who did it, when you did it, even why you did it. And this is really important for compliance, auditability, and many, many other reasons. Yeah, and you can do historical analysis. And as I just said, it's important to be able to query and discover your data. So what we're proposing is to take your analytics and make it fit in the total infrastructure of structured, unstructured data and the knowledge that you have. Yeah? Now let me give you some examples. Let me go here. So one thing we do here at Franz, and I've talked about it before in my presentations, is that we work with a hospital chain in the Bronx called Montefiore. We have data from nearly 3 million patients and about 10 years of data. And so, I mean, that's a data scientist's dream. And one demo that I've given a lot, and I'll do a short version of it today, is where we actually look at all the odds ratios between events, where an event can be the medication administration or a test or a procedure or a diagnostic. Yeah, so the demo that I'm going to talk about is about odds ratios between symptoms. Yeah, so imagine you have this huge database with all these symptoms of 3 million patients over time, and say you wanted to know that if a person has allergy to peanuts, what are the other things that are surprisingly often go together with allergy to peanuts. So what you do to compute that is you take all the symptoms, in our case actually the billing codes for symptoms out of the database. You compute the co-occurrence between every pair of diagnostics, and then you compute the ratio between the actual co-occurrence that you see and the co-occurrence that you might expect based on the distribution of the underlying symptoms. Yeah? And so here is a visual query that I've demonstrated many times before. So this is a typical visual query that we can do where we say that if I have allergy to peanuts, give me all the odds ratios to the top 5 other things that go with allergy to peanuts. Yeah? So what happens here, this is our query screen. It gets translated into, when I do the query, in this case it gets translated into Prolog. Actually, let me go back. I wanted to do this in Sparkle. Let me turn this into Sparkle. Run the query again. Okay, so here we see that the visual query actually got translated into Sparkle. And note that we are talking about ICD-9 terms here, and this is the code for peanut allergy. And then what we see is that the things that most often go with peanut allergy are dermatitis due to food taken internally. Actually, the odds ratio is 210. That means that the co-occurrence of dermatitis and peanut allergies is 210 times higher than you might expect based on the distribution of both dermatitis and peanut allergy. The other things that go with peanut allergy are asthma, 2 types of asthma, then another type of dermatitis, and then finally another lung-related thing, in this case acute upper respiratory infections. Yeah, so here is the top 5 things. I can turn it into a graph. And then, so here is just to illustrate what I've done. Yeah, I had all my symptoms in the database. I did an analytics on top where I computed the odds ratios between every pair of symptoms. Then I can do and then I put these odds ratios back as triples in the database. Yeah, so now I have a graph that describes the relationship between almost every type of symptom. I can do queries on top of that, but I can do even more. Yeah, so I found that allergy to peanuts is related to these symptoms, actually billing codes here, but I can go further. I can say, well, let's select the 2 predicates from and to. Let me select these symptoms here, and let's find the shortest path between each of those. Yeah. And so now what I have is I have a cluster, and I see that the new the things that connect these symptoms together are symptoms that are still very much related to these, obviously. Yeah, so we have allergy to other foods. Let me make it a little bit bigger. Viral pneumonia, allergy to milk products, a common cold, and eczema. Yeah. So what I did is I created a cluster around allergy to peanuts based on analytics. I hope you also see. So one, I can do queries on top of my. Well, so I put my analytics back in the database. Now I can do queries on top, and I can discover other relationships by doing graph analytics on top of that. Yeah, and I can do this for. So we have about 20,000 billing types of billing code in our system. I can take anything I want. Another thing I could do is, for example, like a housing. Yeah. This is a more complicated query where we say that if a person, this, by the way, this is in the Bronx. A lot of people in the Bronx are homeless. So like a housing is a billing code that hospitals use to justify certain types of treatment. And so basically I can ask, what are the top 5 things that go together with like a housing, and then can these, and how are these other things related themselves through odds ratios? Yeah, and I can run this query. I get the out, so this is the query that was built for visual picture. I can create a visual, I get the results here. It's a beautiful graph, but unless you visualize this, it doesn't mean anything. So I visualize it. Now I have a visual version of this, and then just for fun, let me do it this way. Yeah, let me make it a little bit smaller again. Yeah, and then you see that lack of housing is highly correlated to cocaine abuse, cocaine dependence, continuous use, and acute alcoholic intoxication. Yeah. So I hope that makes some sense. We put the data back in we put the analytics back in the database, and now we do further research on top. But it gets even better than that. Okay, so this is the demo I do. This is my first demo. Let's go back to the presentation. I just talked about odds ratios. I have these slides in the presentation. I'm not going to explain anything more about odds ratios, but we'll give out this presentation, so I'll just leave this in so you can study this later. Okay, so another technique that we do is association rules. The data scientists in our audience obviously know about this technique. Yeah, I mean, it's usually used for retailers, that if I buy onions and potatoes, then I'm very likely also to buy burgers. Well, you can do the same thing for diseases and symptoms and procedures. And so here we see a graph example of association rules. Well, the first thing you have to note is we have a session for data science. We gave it the name Analytics 4, just a number. We have a little bit of a description. It's of type analytics. This is the person that did the research. We selected part of the data, and we did it at a particular date. Yeah, and then here's the actual content of what we find. We see that if you have acute kidney failure and you have severe sepsis, then very likely you're going to get unspecified septicemia. And if you have unspecified septicemia and septic shock, then very likely you're going to get acute respiratory failure. So this is really interesting to look at the entire picture, because it's almost like you have a Markov chain in your data where you can see how multiple symptoms lead to new symptoms, where in combination with other symptoms lead to other symptoms. So you get almost like a force field in your database. And again, realize we did analytics, we put it back in the data as a graph, and now you can discover amazingly interesting relationships. Another thing, a machine learning thing that people do a lot is k-means clustering. And again, I'm not even going to explain what it is. It's just a multidimensional clustering technique. I'm actually going to do a little demo for this later. But I'm assuming by now that everyone knows what it is. So here's an example that we did on our data set. So again, here is the metadata on the left side. I hope you can see my mouse move. This is the metadata about what we did. We actually did a very simplistic k-means on all the symptoms in our database. And so what is the top cluster? Well, the pink parts are the factors. So we see that in this case the highest one is other and unspecified hyperlipidemia, yeah, or another big feature in this cluster is diabetes. So here is the factor, and then it links to a billing code. So the blue little thing is a billing code here. And then here you have the, I have no clue how you call this color. Is it like brown, or is it? These brown ones are actually patients, yeah. So this is a patient that has, say, a particular encounter with a particular diagnosis, which is coronary atherosclerosis. So a cluster both has these factors and then every patient that links to this cluster. And so we can look at one patient and we can, and this is not medically relevant, but just to see how all these types of analytics can be combined anyway. I now could say, okay, what is the shortest path between these two symptoms based on, say, odds ratios? So I can click on that. Yeah, and now I see the odds ratios that I just demoed in my previous little demo, yeah, and I can see the statistical relationship between these particular two symptoms. I hope this makes sense. This is not medically relevant, I want to say this again, but it shows you the power of having all these results of analytics and now looking at different ways at your same data sets. Okay, now we don't do this only for medical. We have I actually in the near future I'll give a talk about like 4 or 5 use cases where we use probabilities in AllegroGraph for interesting POCs and running systems. Here's one that I really like, and that is to compare products that were sold on eBay, Amazon, and Google Shopping. Now, one problem is if you want to compare, if you're a consumer and you want to buy a particular anti-wrinkle cream, it's incredibly complex to compare products from different vendors, and partly it's done on purpose, yeah. So you can't compare, so you can't look whether you're paying too much or not. So what we did for a company is to actually look at all the anti-wrinkle creams that are available on Amazon, eBay, and Google Shopping, and actually look at about 10 features: picture, the textual description, the use of product codes. By the way, if there's one thing on earth where people cheat with, it's with product codes. But anyway, so we take all these features, we compute similarity between products, yeah, based on these features, using some machine learning techniques, and then we can again do queries where we, for example, find similar objects based on, find low similar products that use the same product codes in this case, for example. Anyway, this is just an example, and I'll talk in the future more about this particular use case. Very interesting. Anyway, so let me now go to the meat of this presentation. So, so if you're a data scientist and you want to work with a triple store like AllegroGraph, and you want to do data science and you want to put your results back in the graph, how do you do that? So here's a picture. I apologize for the picture. I didn't have much time, but I hope it gets the idea across. So you start with your data in AllegroGraph. You always do a Sparkle query to get the features out of your data. And obviously you could store the results in a comma-separated file, because then R, Python, and Spark can read from that easily. But we've gone a little bit further, and we made sure that in the interfaces that we provide, Sparkle queries go straight to data frames, because as the data scientists in the audience know, is that it's the shared common data structure between every analytical package, whether you use KNIME or Spark or Python, R or Scala or whatever. You always work on data frames, and all these systems make it easy to switch from one data frame to another if there's a little bit of a difference between two languages. So, and what I'm going to demo is how in R I can create a data frame to Sparkle from AllegroGraph, and then how I can create a result and put Becker's IDF triples in AllegroGraph. Yeah, so this is the cycle. So the first interface I want to talk about is AllegRo with the big R. It's an interface from R to AllegroGraph. You can find it on GitHub. It's open source. It's very well documented, and you can clone or download it from here. And there are some other R packages where you can do Sparkle queries, but we have literally, well, in this case, this package provides literally every REST call you can do against AllegroGraph. So the entire AllegroGraph API is available in R. So you can create open databases, add, delete, do adds, do deletes, queries, whatever you can do with AllegroGraph, you can do straight from R. And as I just said, you can create data frames from get statements or Sparkle queries, and it will work with the free AllegroGraph trial version. So let me do a little demo here. Let's see here, where do I have my R? The R is here. Okay, so say I have a database. Let's see if that I have here. I'm logging into AllegroGraph that runs here on my laptop, and the demo I want to give is very simple. I just want to show the correlation between the length and height of people. Yeah. So here are some statements in our database. Yeah, I have a person 1 with a particular height in centimeters and a weight in kilos. Person 2, height in centimeters, weight in kilos, etc., etc. Yeah, so here is our data that we want to work with. And going back, what can I do? The first thing I can do is I can actually load the AlleGro. So you have to download AlleGro, and then you load it in your RStudio. Oh, by the way, I should have mentioned that. Sorry, I forgot. This is RStudio. This is one of the probably most common data science UIs on the planet. And almost every student that learns to do data science and statistics will work with this RStudio. Then say you loaded the library AllegRo, then you start the service to AllegroGraph. In this case, it's on my machine, this port, username, password on my laptop. So now I have a service object here, and let me see what catalogs do we have on our service. And you see that we have a system catalog here, a real-time, and then the dot, which basically means a root. And so those are the 3 catalogs. And then within catalogs in AllegroGraph, you can have multiple repositories. So let me open the root catalog. And let me see, what are the repositories that I have in this catalog? Yeah. So here are all the demos that I usually give, all kinds of demo databases that I have in my database. If I wanted to switch back here, go back here, and basically you see this is the web interface here, all the databases that I can see. Yeah, but I'm showing you the programmatic interface. And then now, how many tuples are there in this database? Well, there's a get size parameter. So I can just say, give me the size of the database. There's 202 tuples in there. And then to get to the heart of this tiny little demo is, so I want to create a data frame where I read in the height and the weight. So all I have to do is something like this. I have a Sparkle query that says, select height and weight, yeah, where there is a person. There's the height, and a weight. I want to clean up the results, because the results will have the IDF data type, so I'll give you just clean numbers back, make sure they're the right data type. And so once I execute this query here, I have a data frame. So I do this. This here. So I have a data frame. If I wanted to show the head of the data frame, I would do this. Just let me take this one here. I have data frame. Yeah, so it's the top things you just saw in the tuple form. And let me plot it. So I can just say make a plot of height against weight. Yeah. And this is what RStudio is really good at, to give you all these plots in a very, very simple way. And then the other thing you wanted to do is say you want to compute the correlation between the height and the weight. Well, this is just how you say that in, you have the data frame. So you just can compute the correlation. And on the right you see here it's 0.88 in this part on the top here. And if I wanted to, I could put the data already back in the database. I would say add a statement based on this connection, make a subject as height weight correlation, the predicate is value, and then the actual object is the correlation. I add this in the database. And now if I go back to the database and I go back to people, a few statements. Let me give you all the statements. Actually, give me 500 back. Yeah, then at the bottom, you see the height weight correlation is 0.88. Yeah, so that is my little R demo here so far. Now let's go to the Python demo. So as I said before, Franz is maintaining an AllegroGraph interface. A Python interface to AllegroGraph. If you want to look at the code, you can go to GitHub, and you'll find the latest version just from a few days ago on the website, AllegroGraph Python. It looks very much like the Sesame interface, by the way, for people that still remember that one. But please don't. Well, you can download it, of course, but if you want to use AlleGraph Python, it's actually better because of all the dependencies to use the Anaconda package manager for Python in R and Scala. Yeah, so most people probably in the data scientists know this website. Yeah, where you can see that Anaconda is this data science platform powered by Python, and the 100 most popular Python R and Scala packages can be found there. Actually, it's about 720 packages that can easily be installed. If you want to install it, yeah, just first create an environment. Well, first download Anaconda, install it, and then this is how you create. This is important here because it's a little bit different than most packages, but you create, in this case, an environment called test environment. Using a Franz channel called Franz Inc, and then you get the AlleGraph Python from there, and then you get your favorite packages like NumPy, Pandas, and Matplotlib. And then when you want to activate the environment, you do source activate test environment in Linux. If you use Spider, you can just do it in the GUI. If you want to get a very particular version of AllegroGraph, you have to specify it like this, AlleGraph Python 6.0.20, or you can just do an update and then you get the latest version. Yeah. Well, let me do a little demo. I'll do first a correlation demo. Again, the one I just did in R, just to see how similar they are. And then, of course, there's no way anyone in this world can do a machine learning demo with at least doing the iris example. So here's the iris example. Most people know this. Yeah, this classical challenge to classify 3 types of irises, the Setosa, Virginica, and versicolor, and you do it based on petal length and sepal width. So the sepals are the big leaves that are usually green with most plants, and then the petals are the upstanding little things here. Yeah. So anyway, let me do the demo. Going to my Ubuntu box on my laptop. First, let me show you the data that we have. Actually, it's iris. So this is the database, 750 statements, and let me just show you. Yeah, so we have 450 data sets. We have, say, take iris 149. We have petal width, petal length, sepal width, sepal length. Yeah, in these form. And so we have 150 flowers with these different values. And then I'm going here. Actually, I'm now off my script because I promised to go first to the correlation example.
Yeah, go right to this.
Huh? I'll go right to this one. Okay, that's more fun actually. Yeah. So I have this database. So let me open the triple store iris. It's as simple as this. Yeah. So I go here, and so on the left I have my screen with the program in it. On the right, I have the Python. Actually, let me just have the Python. Oh, sorry. Right here. And so at some point, I started I did this what I just described in my demo, source activate get, which in this case the environment that I'm using. Yeah. Then I started the Python. Let's see, did I start the Python? Oh yeah, the Python. I click Python, and because what you see here, get, this is the environment that you started by doing source activate. And so once you do this, you get an environment. And now if you start the Python, it will actually start it in the environment that you create with all the packages that you loaded. So it will take care of all the dependencies. And we see we're running a Python 3.5.2 here. And then let me go to the bottom. So if I want to do my k-means on top of the iris data, I first have to open the database. So now on the right I have an open tuple store. Then I create a data frame just like I did in R. So I said the data frame is run Sparkle to data frame, and this is the Sparkle query, yeah, where we say select petal length, petal width, sepal length, sepal width based on where X has these features. So if I create this, so now I have a data frame. Yeah, I could say print df. Okay, probably df. Yeah, here you see we have a data frame, row number 149, and then the 4 values that I talked about earlier. Then we do our k-means. I'm using a very, very simple version from the k-means from the sklearn package. So I say km is k-means number of clusters is 3, and then I applied it to the fit the data frame as a matrix. Yeah, so this is just one line to do your cluster analytics. So let me execute that, F8. So now I have this. And then one result is that, so remember here we have these 150 lines with data. What I get back is also a labels array list that for each of these lines here will tell what the cluster is that we actually want to have, that it assigns that particular line to. So I execute the labels. I could look at the labels. Here's the 150 labels. Yeah, so it's 0, 1, or 2. And then, so now I have the label, so now I know what it belongs to, and now I do my cluster assignment. So I put the triples back in the database. So first I delete some triples because I'm doing it again. I open a little file. I could put it directly in AllegroGraph, but I like it to do it this way. I create a new file, and then from 0 to 150, I make a new iris subject of the triple here. Then I get the C member of the labels, and then I assign the names here. And then finally, I write a triple, where I take the iris with the predicate name, and then the name that we found here. I close the database, I load the triples, commit. Yeah, so I can assign the cluster. Let me do that. Assign a cluster. So now I've done this. So remember when I showed you the picture before of we had 750 triples. When I go back here, we now see we have 900 statements. Yeah, so now we have all these data. These triples are in the database. The assignment of what name a particular row had in my database. And now I can do additional queries. I can say, well, I want to know the average petal length of each of the 3 types of irises that I have. Remember, we started out without having these names in the database, but I did the cluster analytics. I put them back as triples, and I assigned the name to each row. And now I can say, what is the average petal length? Yeah. For each of the types. So I make a copy of this one here. I go to do a query, new. And now I see the different length of the petal lengths for Virginia, Setosa, and the first you call it. Okay, so that concludes my demonstration here. In the very near future, we'll give some more talks. One issue that I want to talk about is a more formal ontology to represent analytic output. There's a lot of scientific research right now where people talk about sharing and reusing data from scientific experiments. How do you actually store? So there's actually a big, some really big research projects going on this. There's some practical proposals, especially in our healthcare research. We need like a more formal ontology. So that's something I'd like to talk about. Another is KNIME as a data science framework. So KNIME is a package, an open source package where you can create modular workflows for machine learning, where each module here takes as the input a data frame and gives an output of the data frame. And the module itself can be written in any language, whether it's R, Python, or anything else. And you can just click them together. And on the left you see all the types of machine learning and analytics that you can do. So we're going to talk about that. And then we're going to talk real soon about the new distributed AllegroGraph that we have, where we can literally deal with trillions of tuples, and where we can do Spark on top of our data set. Actually, the odds ratio demo that you see, I'm going to demonstrate that how we do that with Spark. So those are the things we're going to talk about real soon, and now I would like to take your questions.
Okay, looks like the first one I got here is, will the demo scripts and data be available?
Yes. So actually, the R script will be available. The Python scripts also make available, but I'm using a kind of my own Python layer on top of our official Python layer. So you'll have to figure out how to do this yourself, but I will make it available.
Okay, let's see, the next question is, how do I do the odds ratio in R or Python?
Well, actually we did this one initially in Lisp on a big memory machine, and we do it now in R. It's really a lot of data, and it was too big for R to do it over all the symptoms. And in Python you probably could do it, but I haven't tried it. We just went straight to Spark.
Let's see, another one here is the Graph demos. What sort of new things can we expect from Graph?
Disrespect? Well, the one thing I didn't, what can we, one thing I really like, I don't know if people have seen the Graph uses, but we have this particular kind of rendering, which is incredibly useful, where we use shortest path, from any start node you take, and then when you go to the end, you actually still can see how you can get back to your beginning node, which is a really powerful feature. And another feature that we're working on is where we can replace all these things with pictures. For many years we could use pictures instead of these nodes here, but now we also have a feature to find pictures on the web. So how can I demonstrate that? Let me show you if I can show that. Let me try that. Let's see this one here. If I do this, set match. Set child off. But I'm linking the billing codes to a terminology system. Let's see here if there's anything interesting. Child 6. Yeah, so I can actually take anything that has a label. I can do something like Control B, and I get a picture from DBpedia that goes with drug eruptions. Yeah, so you can actually add pictures. I can look at allergic asthma, and I can do Control B, and I get a device to measure your oxygen inflow. I guess that's what it is. Anyway, it's a fun new thing, although it's actually better if you create your own picture libraries and link them to your nodes, and then you can actually replace the nodes in Graph with pictures. Oh, that's a new thing. Yeah, okay. All right, anything else?
Let's see. Here's why is this better than using Neo4j?
Oh, that's a tough question. So you actually have to look at the picture that I started with, I think. Yeah, if you look at this picture here, let's look at this picture here. So in order to take any structured data and unstructured data and the knowledge, where knowledge is terminology systems, which are almost always written in RDF, yeah, and take linked open data, which is all written in RDF, then you want to link all that knowledge in your data infrastructure, then I mean, a semantic graph database is really the only option you have, unless the Neo4j people reinvent semantic graphs on top of their database. I think that's the best answer.
Okay.
In this case. And then finally,
could you please describe some of the ways you trace the provenance of an analysis? What sort of meta-analysis do you do most commonly?
So one thing that we hope to talk about real soon is something that Montefiore runs in production. It's a system where you compute respiratory failure up to 48 hours before it really happens. And it's many times better than doctors and nurses at predicting this. But it's also a big danger because you actually make now real-life decisions based on a machine learning model. So we have to do really precise provenance. And so we literally, so this system is based on a random forest network that takes in 46 different types of variables. So we actually store for each run of the random forest every variable it's based on, from what system the variable came, what rule we used, what the output values were, so everything. So then we can go back in time and we can actually use it for validation. Yeah? So if you ask what kind of metadata we do, we use this in this case for validation, but also historical analysis. And I think that's all I want to say about that right now. Okay, so thank you very much for your attention. And send me email, or send us email if you have any more questions. Okay, thanks.